Good morning. Earth Science, this is for the 22nd of April, and we're moving along. Yesterday, we studied the three major models of the universe that they explained in those terms. The first was the Aristotelian, then you have the Ptolemaic, which is a modification of the Aristotelian, and then you have the Copernican model. So we want to start and pick up from there. And you should have your book. I want you to have your book open to 692 to follow these, because these are very difficult concepts. And you should read the chapter and then study your words. Yesterday we left off with Galileo, and I said that he was the father of the experimental science. And he observed the motions of the planet with the newly invented telescope, which we studied in the last chapter, and proved that the heliocentric model of the solar system was correct. Stated that terrestrial gravity causes all objects to accelerate the same amount regardless of their mass. Remember the dropping of the rubber ball or the steel ball from the tower? They fell at the same speed. And the rate of the acceleration is constant. There was a famous astronomer, Danish, 1546 to 1601, Tycho Brahe, if that's how you pronounce it. After years of careful observation, Brahe discovered how planets moved in their orbits. All planets, including Earth, move in elliptical, not circular patterns. But he didn't understand all these calculations and all these things he had, but he couldn't put it together. He had a young mathematician called Kepler who came and worked with Brahe's data. Kepler confirmed the Copernican universe. Remember, at that time they thought everything was our universe, and calculated the true shape of the solar system, discovered the three basic laws of planetary motion, and laid the foundations for Newtonian physics. Boy, Kepler to Isaac Newton. But let's talk about these laws of ellipses. In my notes way back in chapter 5, in a footnote, I talked about these different laws. So if you want to go back to chapter 5, you can find it. The laws of ellipses, what does that mean? Lex legis, feminine third, law or rule, and Greek ellipsis, to be wanting and lacking. Lacking what? A perfect circle. So Kepler's first law, each planet orbits the sun in an elliptical path. Wow! So what is an ellipse? An ellipse is an oval whose shape is determined by two focal points within the figure. So Dr. Wood put that on the board for you way back in the earlier chapters. Now, if you go and talk about the ellipse has eccentricity, the degree of elongation of an elliptical orbit. Symbol is small e. If gentlemen, if the elliptical orbit is very, very, very pronounced, it becomes a straight line. And as it becomes less elongated, it becomes towards a circle. So you can imagine that the eccentricity, the degree of the elongation of the elliptical orbit. Okay. Now, the focus are these points. One of the 2 points within an ellipse that determines the shape of the figure. How perfect is the circle? How unperfect is the circle? Now, we've had these words last chapter. You're going to get them again and again. Perihelion, peri, near, helios, sun, the point in the orbit of a planet at which the planet is closest to the sun. Aphelion, you had the point in the orbit of the planet at which the planet is furthest from the sun. You already had last chapter, astronomical unit. An average distance between the Earth and the Sun approximately 153 million kilometers, or in our system 93 million miles. Whew. Now you have a second law. Law of equal areas. That's very complicated. You have to read it in your book, and that's on page 692. So follow those things in your book all the way through. And then you have Kepler's second law. Each planet moves faster when it is at perihelion and slower when it's at aphelion. Now that makes a lot of sense. Why? If the sun is there, great gravitational pull, and you're closer to the sun, you're going to go faster in that orbit. And as you go to aphelion away, you're going to slow down a bit. And as you go around again and you get closer, you're going to speed up, and then you slow down. That is Kepler's second law. Now this is the hardest one, law of periods. So the period is how the amount of time. So Kepler's third law, each planet moves in orbit around the sun at a speed that is proportional to the distance of its orbit around the sun. And that's his wonderful formula, k times r radius cubed equals the actual distance, proportional distance. And he was able to use that formula to help figure out how far all the other planets are from the sun. Very complicated. If we could have the next word, how far do we go today? We go to word 27. Okay. Word 26, orbital period, the time required for a planet to complete one revolution around the sun. And then you have the word inertia. Ooh, I love this word because this is what Isaac Newton used, and we'll talk about that in a minute. Inertia, the tendency of an object to resist being moved, or if the object is moving, to resist a change in speed or direction until an outside force acts on the object. So do these review questions on page 694. Now I'm going to turn the lights on, and I want to explain a few things. I'll turn the lights on. And this is most important. So I want you now to turn, you got on page 692 and 693, the laws, and then go to page 694. This is the most important thing. Newton's explanation of Kepler's law. Woo! And it starts out with inertia, the tendency of an object to resist being moved, or if the object is moving, to resist. Now, look at me. Let's pretend the camera is the sun. Woo! Okay. Obviously, if I'm going around, I want to go that way continually. But no! The camera, the sun, is pulling me in. And it's pulling me in. And I want to keep going straight. Pulling me in. I want to go straight. So the combination of those two forces, the gravitational pull of the sun and me moving in orbit, wanting to go straight, the sun pulls me back. So the combination of those two things is what Newton explained the motion of planets. And if you go to page 694, Newton's model of orbits, because a planet does not follow a straight path, an outside force must cause the Earth to curve. The outside force is the sun, of course, and he used the word gravity. So he realized that this attraction force between any two objects in the universe is gravity, gravity, gravity. The gravitational pull of the sun keeps objects such as the Earth and other things in orbit around the sun. While gravity pulls an object toward the sun, inertia wants it to keep moving in a straight line. So I hope you read this very carefully to 694. Answer those questions on page 694. and then we'll see you on the following day for the next section. Thank you very much. I miss you all. Wish you were in my class. Goodbye.